Fraser Stoddart, welcome to Nobel Week in Stockholm.
Thank you.
All Nobel laureates are asked to bring an artifact to donate to the Nobel Museum here in Stockholm. What did you bring?
Well, I brought some of my toys that were constructed when I was at the University of Sheffield. These particular models date to somewhere in the mid-80s. They are showing signs of wear and tear. The history to them is that they were made in the workshop of the chemistry department at Sheffield, which was one of the very best, I think, in the whole of England. So they produced these models very quickly and easily.
Can you show what it is?
Well, this is some sort of metal bar, and there's magnets inserted in each end. And what I'm doing at the moment is putting these what were called stoppers when we come to describe this dumbbell. So this is the rod portion. These are the two stoppers. The two stoppers are the artifacts from the cisterns of toilets. It's the ball cock that floats up and down. So I think this was quite imaginative on part of the people in the workshop to use that principle. And then that rests there. And if I take one of these rings, then we go from what is a molecule here, a dumbbell, and one of the ways that we devised of making this particular 2-rotaxane, and it prefers to go to the green unit, is to clip round the green unit like this. This gives us a 2-rotaxane because now we have the dumbbell, which is...
What did you call it? This gives us the...
2-rotaxane.
2-rotaxane.
So it gets its name from rota, Latin for wheel, and axis, Latin for axle. So this is the axle, if you like, and this is the wheel.
So this is the chemistry.
This is chemistry,
that you are building right now.
Right, and this is an expression of the so-called mechanical bond. The blue part is not linked by classical chemical bonds, covalent, coordinated bonds, any of these bonds to the dumbbell portion. And so this is now another molecular world. We started off with the dumbbell as a molecule. We started off with the blue ring as a molecule. But when we clip the blue ring together on this dumbbell, we then create another type of molecule.
And why do you want this molecule that you create in this shape with a ring and a rod?
Well, it gives you the basis for having a switch. So the rod portion contains two recognition sites. We sometimes call them stations. These are the places where the ring prefers to sit at any one time. Now, when it's sitting there, it's shivering back and forth in the real world. And we have a green site, which is associated with something called tetrathiafulvalene. And the blue ring prefers to sit there 9 times out of 10. So this is 9 times there and only 1 here. So it is what we call a non-degenerate rotaxane, or a molecular switch. So we have the first inkling of a molecular machine. It's not a machine yet, it's a molecular switch. And what we can do is we can speak to the green unit, we can take electrons out of it, and I should paraphrase what I'm going to say by telling you that there are already 4 positive charges in the blue unit. And if I take 2 electrons out of the neutral green unit, then we have like charges repelling each other, and so the ring decides that it would be better off to move there and spends literally 100% of its time there, while there is charge on the green unit. But if you deliver electrons back and make it neutral, then this ring will make its way somewhat more slowly back to there.
So you can steer the blue ring, yes, on the rod.
And you can make it switch.
And make a switch.
And you can put many of these into a device, and you can then create molecular random access memory based on this principle.
So you can make movement and memory, and it's a
Yes.
fundament for the molecular machines.
Well, we're not at the machines yet. This is molecular electronics. So we have something that switches. To go to molecular machines, I don't have a model to explain that phenomenon. I'm going to talk about it on Thursday in my lecture. One has to go a step further. One has to do work. A switch does not involve doing work. We started there, we went here, we went back there. But we have to go a step further when we go to make a molecular machine.
Okay. Of course, is this something you want to show too?
Well, I just want to mention that this is 2 interlocked rings, and this was our first contribution to this field, as was Jean-Pierre Sauvage's. He described his first 2 catenates, so he had a metal involved as a template. We dispensed with the metal and only used recognition between organic components. So our 1989 publication in Angewandte Chemie was our first major contribution to the field. We had used, however, I have to say, a whole decade choosing the right chemical constituents for the blue component and for the red component.
So it took you a decade from the first publication in this field for you to get to your discovery?
Well, it's always very difficult to say when it started, but I would say 1981 was when we started the pursuit to get the components. And these components, ironically, came from my spending a period of 3 years on secondment to Imperial Chemical Industries, ICI, as it is in shorthand, corporate laboratory in Runcorn in Cheshire. And it was there that I got introduced to ultimately herbicides called paraquat and diquat. These 2 chemical compounds were used in admixture for many years to just wipe out green life, so you could use it to clear your path. They exported it to the United States to
herbicides.
To Idaho also to get rid of the potato greens before the machinery came in to harvest the potatoes. And so for many years, this was the most important herbicide on the market. And it is these components, diquat and paraquat, that get built into these
really
artificial molecular switches. So,
interesting.
Of course, we use the same principles as biology uses ultimately in terms of interactions between aromatic rings, hydrogen bonding, and so on and so forth. But that was where the bits and pieces came from. It came from my time at ICI.
But if we go back in time a little, what brought you to science? I understand you grew up on a farm.
Yes, I grew up on a farm about 12 miles south of the capital of Edinburgh. It was a tenant farm. In other words, we didn't own it. We paid a rent every 6 months. My father moved there in 1942, the year I was born, when I was 6 months old. He had come into farming as a student of farming. He had been to the Agricultural College in Glasgow, and the job that he left to go to the farm, being the farm manager of the University of Edinburgh's farms. But when I was born, my parents obviously took the decision that they better be a little bit more independent. And so that's what took them to a farm called Edgelaw Farm, where I spent the first 25 years of my life. We did not have electricity until I was 17 in 1959. So it was quite a challenge, just living on a daily basis. And it was a so-called mixed arable farm. So we grew everything that you could conceivably grow in that part of the world, rather similar, I guess, to what you would grow in Sweden on a farm, potatoes and other root crops, oats, barley, wheat. And then we had a dairy, so we had milk cows, we had lots of sheep, my mother looked after hens. We never had pigs, my father loathed pigs, so it was a very mixed situation.
It sounds like a wonderful way of living, but I guess a lot of hard work. too.
Oh, it was a lot of hard work, but I actually call it the University of Life. It's as important as any of the universities that I trained at, because it gave me the opportunity to get involved in engineering. The first motor cars and tractors were so simple that you could take them apart, and you had to, in order to make them efficient again. They would get coked up with carbon in their cylinders and so forth, and one had to clean them out and put them back together again. So I had a good introduction to engineering, if you like, on a macroscopic scale, on a big scale.
Yeah, so you worked actively on the farm until
Yes,
you were
yes.
25.
Yes, and then I went to Canada, and within, I see, 18 months of my going to Canada, my parents decided to leave the farm. So I was very important, a very integral part of that farm.
But what brought you to university studies?
Well, my parents always had a huge influence on me in respect of putting education very high. I had 3 wonderful years at a local village school with a very good teacher, a woman called Miss Morrison. And this was the type of schooling where all the children were brought together. And when I started, there were 5 of us. There were 4 girls in Fraser. And Fraser learned to knit just because I was in the minority. When I left the school, I think there were 28, 3 years later in 1950. So my parents decided that I should go to a school in Edinburgh. It was called Melville College. And I had the most marvellous education there, both through the rest of my primary and secondary education. And I look back on it, I didn't appreciate it at the time, but I think...
Why not?
Just because my teachers, when I think about it now, could all have been professors at a university. They were very, shall we say, erudite people with great teaching skills, and it went far beyond the classroom. They would take us to concerts, they would take us on hikes, they would, it was just absolutely marvelous when I think back on it. So I'm actually going back to not quite this school. It had to merge because it was a little bit small with another bigger school sometime, I think, in the 1970s. And I'm going back to that school on my way back from Stockholm to Chicago.
Oh, wonderful. And how come you choose chemistry? And at what stage did you choose chemistry in university?
Well, the story is the usual one. I had 2 marvelous chemistry teachers at Melville College, and I just got absolutely fascinated by the subject as I saw it then. I was never very switched on by smells or bangs, so it was a process over many years of falling in love with the subject, and I think it was more the wonder of doing something in life that might end up being useful, and also allowing myself to be creative. And I think this is the science where, since you make the things that you work with, you're also part artist. And I think that's, without actually maybe consciously realizing that, this is what subconsciously drew me into chemistry more and more. So the story about why I got into research is quite interesting because it plays back to the farm. So I'm in my 3rd year at Edinburgh. It's 1963. An analytical chemist who's running a course has a class of maybe 150 of us, and he makes 2 comments. He says, there's enough cyanide in the lab, and we're going to pipette it to kill the whole of Edinburgh. And we all kind of look at each other and feel terrified. And then the next thing he said, he went over the top. He said, I devised this course many years ago, and it's a 10-year course. Nobody's ever finished it. And, well, the short story is I finished it in 7 weeks. How? Because I multitasked. I didn't do one experiment after the other in a linear sequence. I did 3 experiments at once. And so that brought the opportunity to go into the research lab under the guidance of this person.
How did you get the idea to do all these experiments at the same time instead of one at a time?
On the farm, because on any day on the farm, particularly, say, in the spring, we would be milking cows in the morning. There would be sheep in the paddock close by having lambs. there would be the need to be doing the last vestiges of ploughing in order to sow some oats or barley. Maybe the wheat had been sown the winter before, and getting ready to put the root crops in. And there would be somebody who would need to clean out the hen houses. So there was so many things going on in one day that.
So that was the way you were used to
That was the way I
solving
was
problems.
used to, and I found that the students I was alongside, they were thinking in a linear way, whereas I was thinking it's just like being on the farm. And if I used the same principles that I had been instructed on in many ways on the farm, then I could make this piece of lab work less of a linear situation and finish it a bit earlier.
Going a little bit further in time, do you remember how you got the idea, the thinking of how to make this, what's it called? This
this is called the rotaxane,
rotaxane.
or in more general terms, mechanically interlocked molecules. So introducing this new bond into chemistry that I think Jean-Pierre Sauvage was right in the vanguard of, and I was following. As it's turned out, I think it's a major advance insofar as, I often put it this way, probably every day 1,000 or 2 or 3 new chemical compounds are invented or made all around the world in different laboratories. It's only once in a blue moon that a new chemical, or a new bond, I should say, comes along. And this is a physical bond rather than a chemical bond. So it was waiting to be done. It had been talked about from the beginning of the 20th century. There was so-called chatter in Zurich by some of the eminent chemists of the days, round about 1910. One of these, I think, was Professor Prelog, who was a Nobel laureate somewhere later on in life, of course. And then not much happened until about the 1950s. There were a few forays into making mechanically interlocked compounds, particularly these catenanes. But the chemists of the day were struggling because they were trying to match like with like, and that was not giving them very much success. At very best, they would get less than 1% yields, relying on statistics.
Do you remember the moment, when you started thinking that, maybe I could do it this way?
This was when I was in ICI. It was when I realized that we had the bits and pieces that were talking to each other, that were entering into molecular recognition. And so to be more precise, by pyridinium systems, this is what the herbicides were based on, are pi electron deficient. And then we reasoned that aromatic rings, particularly with oxygen atoms connected to them, would be pi electron rich. And these, we knew, stacked together. This was well recorded in the literature. And so what we were building on, of course, was the work of Jean-Marie Lane and Donald Cram and Charles Pedersen, the people who got the 1987 Nobel Prize in what is now called supramolecular chemistry. So we were building on that in a sort of conceptual way to see if, having brought the pieces together, we could then, as it were, do something to nail them together so that they would either be 2 rings that wouldn't part unless you broke the weakest covalent bond in the molecule, the weakest chemical bond, or this other construct where you have the dumbbell shape and you have 1 or more rings on it, and the rings can't leave because their inner diameter is much less than the outer diameter of this stopper. And so, part of it also came from my fascination with Meccano when I was a boy, and also with jigsaws at an earlier stage when I was a very young boy. I used to make jigsaws by the dozen, pile them up between paper until my mother said, no, they're getting brown, this paper, it's beginning to smell, Fraser, you can't continue to do this. So it was a combination of, if you like, Lego as we now know it in 2 dimensions, and this whole business of Meccano, which was another form of toy that allowed you to be creative. You didn't have to follow the guides lines in the pamphlets. You could create your own object.
So you must have been excited when you started to feel that you were getting close to the
Yeah,
solution.
yeah. But frustrated that it took a decade, almost. It took about 8 years from 81 to 89.
Did you ever think of giving up, that
No,
this won't
no.
work? No.
I did, and I think this is true of many of us are in this sort of situation, take a lot of criticism. My students took it even more so because I guess senior people felt ultimately that they could attack students easier than they could attack me. But you know, in a sense, if you know something about creativity, and I had read some books, it was not surprising that some of these ideas were being held up as, well, it's exotic, it's maybe interesting, but it's not going to be good for anything, all right? So we got a lot of that in the 80s and 90s, and I'm sure that Jean-Pierre Sauvage had the same experiences. Times move on, and it becomes interesting, and the chorus of dissent disappears, it becomes quiet, and then there's a hiatus, and then one day the phone rings from Stockholm.
Yeah. But I understand you also need a lot of self-confidence and believe in your science to come this far. And what more is needed to get this far and actually being rewarded the Nobel Prize and getting this telephone call from Stockholm?
Well, I usually sum it up in a three-line statement. You need the strength of a horse. And that I gained on the farm because I was up at early hours, moving food, turnips to animals, or in the harvest, moving big bags of grain or something. So you need the strength of a horse, which also means that you don't fall ill. Whatever happens, you eat well and you make sure that you're fit, you need the hide of an elephant. In other words, you need to be able to take the barbs, the criticism, and for the most part, ignore it. There might be some things that you would take on board, but for most of it, you've got to say, well, I know what I'm doing, must continue. And then on top of that, and this is going back to the farm again, you need the work ethic of a honeybee.
Why?
Because I don't think many people succeed in science or anything else at a very high level. I mean, we can go to the people who are running recently, one shape or other, in the Olympic Games. They don't turn up there just to do something for a week or two or three. They've been practicing for years.
A lot of hard work.
A lot of hard work, a lot of training. So, I have a great sort of national empathy with number one tennis player in the world today, Andy Murray. And that again is a story of a lot of hard work with an enormous number of tennis players who are extremely gifted that he's had to compete against over the years.
Do you think he or you has been working most hard so
Well,
far?
he has to work hard to achieve what he does in life in a very short period of time, somewhere probably over 20 years at the most. I think in science, and this is almost inevitably the case in chemistry, it's 50 years that you have to work hard and keep your head down and wait and see what happens.
Yeah.
Yeah,
I guess you need a good team to work with too.
absolutely. So,
How do you put together a good team?
I learned over the years. I have a very much open door policy, and I've used this for many decades now. So once we saw that we had a new story to unfold, I would just say to the brightest and best of my students, and that was virtually all of them, between the ages of 22 and 32, go away tonight and think of 39 new ideas that we can talk about in the morning. We'll throw away 38 of them and we'll just deal with the very best one that you come out. Okay. So I opened up the possibility for, in these later stages of my career, for it not just to be my input, but the input of ultimately often 35 people. That's about the size of my group through the 90s and the last 15 years of this millennium. And it is just amazing. There's about 40 of them I've invited to come here. You know, I've just taken people from different eras to represent the creativity of these individuals. And so the postdoc who made Olympiadine is one of these people, David Amabilino, and you know there are many others that the people who are working on the molecular machines in my lab today. There's an Italian postdoc and there's a Chinese graduate student who are just off-scale brilliant. So I've recognized effectively that you put a team together and you allow the brains of 30 people to work on something rather than a top-down approach where you say, I have all the ideas and these are just ultimately pairs of hands or slaves. No, no, no. And part of this is because that is how I was kind of treated as a young scientist. And so I'm rebelling against the hierarchical system that visited me in the early part of my career. And I said, I'm not going to go down that road. I'm going to fashion something that is new. I'm going to make it possible for young people with amazing talent to express their creativity. Well, that just brings me to the next point that I often say, I'm not in this anymore to do research. I'm in this as a professor to teach. And so my main legacy will maybe not be my ritaxanes and my catenanes, but the more than 100 people who are in academia, all spread around the world, the more than 100 people who are in industrial companies and often in high places, and the one or two that are sprinkled in government. And one of them, for example, is the founding editor of Nature Chemistry. And he is here in Stockholm,
Wonderful.
looking after us all because he has a great, of course, connection with the whole of the chemistry community.
Yes, yeah.
So what I'm proud about is the people that have been around me and are, I hope, going to do better than me.
I must ask you, is there anything that you do that annoys your team that they can laugh about?
Oh, there's one or two things. I have turns of phrases that they don't understand, and this is part of the Stoddart legacy, that I use a lot of idioms, and of course people coming with not English as their first language, let's take the Chinese or any European, in fact, might be struggling to begin with to understand what the blazes are you talking about. The other thing is that in order to put out a publication, we very often go through 50 drafts, and of course my red pen treatment of manuscripts is part of their training, and they will talk about it endlessly. How many times have you been red penned? Yeah. But I should add that I do it to myself. I'm giving the banquet speech, and that went to 100 drafts, and it went out to 3 or 4 selected people to quote red pen, and it was improved a lot during maybe about a 10-day period as a result of that process.
So you really like the red pen?
I think, yes, you need comment and criticism to do better.
Yeah. Thank you very much for the interview, Fraser Stoddart, and enjoy the rest of your week here in Stockholm.
Well, it's been a pleasure talking to you, and I will certainly have fun this week. I intend to enjoy every minute of it.